Hey guys, welcome back. We'll continue day 10. We'll talk about catalyst. So you've heard the term catalyst before, I'm sure. So we're going to define catalyst as a species that speeds up a reaction by lowering activation energy, lowering the EA, by providing a new pathway or mechanism. So it's not the same pathway anymore. It's a different way to go. It's kind of analogy, again, crude analogy, flying versus driving. You can drive across the country, or you could fly across the country. Well, the plane would be definitely a catalyst that would get you there faster. You still end up in the same spot, hopefully, but the catalyst will get you there much faster. So the catalyst, very importantly, is not. So a catalyst is not consumed in the reaction and is not present in the overall equation. However, it may be present in the rate law. So how do I know we have a catalyst? So if you look at the reaction arrow, a lot of times your catalyst, put it orange right here, will go right there. That's where the catalyst can go, above or below the arrow. A lot of times the arrow, there's extra information, whether it's the solvent. If, let's say we're running a reaction in methanol instead of water, well, you'd put methanol below the arrow maybe. Maybe the reaction has to run at 60 degrees Celsius or 200 degrees Celsius or whatever the temperature has to be. That can be in the arrow too. And if you have a catalyst, a lot of times the catalyst is above or below the arrow. Just let us know that the catalyst is there, but it's not actually in the actual chemical change, right? The catalyst should not undergo a chemical change. There are two types of catalysts: heterogeneous and homogeneous catalysts. So for heterogeneous catalysts, they are in a different phase than the reactants. Spell reactants correctly, that always helps. Whereas the homogeneous catalysts are in the same phase as reactants. So that would mean, for example, in solution, not in solution. Your catalytic converter in your car is a heterogeneous catalyst, where you use platinum or palladium to catalyze the exhaust into more safer gases coming out due to incomplete combustion and whatnot. Homogeneous catalysts, right? Good example, iodide and peroxide. So we have an overall reaction here. 2H2O2 aqueous going to break down into O2 gas and 2 waters. Has a rate equal K times the concentration of H2O2. That's the rate law. Now if we add I minus as a catalyst, things happen. It's the same reaction, but a little different. It's a different way to get there. So we have H2O2 now plus I minus going to H2O plus IO minus, which is very much analogous to ClO minus. ClO minus is hypochlorite, so IO minus would be hypoiodate. And then step 2, so that's step 1. And then we'll have step 2 here. And step 2 would be H2O2 plus this IO minus going to H2O and O2 and I minus. So now if step 1 is, let's say step 1 is slow and step 2 is fast, the rate is equal to K times the concentration of 2 species instead of 1. I minus will be in there with the hydrogen peroxide. How fun is that? So it's a different pathway. And if you look, I still have this guy right here, IO minus, that's an intermediate. See how it's produced, then consumed, where my catalyst is consumed, then produced. So that's different. So that's the big difference there. So if we look at a figure here, right, here's the difference between, for example, ozone and oxygen going to 2O2. There's the uncatalyzed pathway with the activation energy. We'll do it here. So the uncatalyzed EA is that big. Whereas the catalyzed EA, if that one's slightly bigger, I don't know, EA1, EA2. And so it's a lot less activation energy to make the reaction happen. So that's all, and it's a new mechanism, 2-step versus 1-step. So that's all a catalyst is. There is a problem. So let's do some problems now to finish up this chapter. Alright, so we'll start with 73 and then 74 and then move on from there. 73 says consider these two gas phase reactions. It says if the reactions have the same or identical activation barriers, that means EA is the same, and they're carried out under the same conditions, which would you expect to have a faster rate? Well, this goes back to the Arrhenius. K equals A e to negative E A R T, right? Same conditions. So T is the same. R is, of course, the same. Identical activation, right? EA is the same. Okay, which one would have a faster rate? Well, it comes down to this guy, right? And basically comes down to the collision frequency, right? So if we break down A into collision frequency and orientation from 0 to 1, right? Where 1 is any orientation and 0 is strict, right? The collision frequency is probably going to be the same or similar for both reactions because they're in the same conditions. So let's talk about orientation factor. If we look at A bonded to A, and B bonded to B, no matter how AA and BB hit, green and blue are finding each other. Versus A, B, C, and D. Now for equation B, A and C have to hit each other. So A and C have to hit, and B and D have to hit. One of those two, right? So if B and C hit, it doesn't work. So this would be any, and this has a little bit of strictness to it. So I would say that one would have the faster rate, right? Because it has a little bit less strict. Now let's be honest. Equation B would be pretty fast, right? But A would be faster due to like the orientation factor being closer to 1. In 74, which would you expect to have the smaller orientation factor? Right? The smaller orientation factor would be more strict. So which one's more strict? Well, we got O and N2. So O and N. No matter what happens, O hits NN versus NO hitting Cl2. And if N has to hit, if we have to hit O, if O here has to hit Cl2, that has a more strict orientation factor. So I would assume that B here would be the one that has a smaller orientation factor. 94. So consider the reaction when hydrogen chloride adds across the double bond of ethene. Alright, so you take organic chemistry, ethane, all single bonds, ethene, double bond, ethylene, triple bond. So we have the double bond, and HCl is going to add. So let's draw a picture of this. HC, HC, HH. Those bonds are staying. Those bonds are going to be broken. H and Cl are coming in. Right? One of the orange bonds is breaking. And it looks like what's going to happen is these electrons right here in orange are going to go back to chlorine. H is going to go to one of these carbons, and one of these electrons are going to go there. Then chlorine, doesn't matter which ones, in step 2 looks like going to add. That's what it looks like it's going to do. Alright, that's what it looks like it's going on. So step 1 in pink, step 2 in green. So looking at these questions, based on the energy diagram, determine which step is rate limiting. So I'm only going to look at EA1 and EA2 here. EA1 and EA2. And which one happens to be larger? Is it EA1 bigger or EA2 bigger? Well, there's EA2, there's EA1. This line looks much bigger than this line. So I'd say EA1 is bigger. So that means for A, step 1 would be limiting. What do you expect the order of the reaction to be based on the proposed mechanisms? So if step 1 is rate limiting, step 1 would be slow, and step 2 would be fast. So the rate law comes from step 1. Rate equals K, concentration of HCl, concentration of H2C, CH2, or C2H4, however you want to write it. That's what I would expect. And it's also first order. So it's overall second order overall. Right, first order with respect to HCl, first order with respect to ethylene, and second order overall. C, is it the reaction exo or endothermic? Well, that looks right there is delta H. Delta H is going down, so delta H is negative. Negative means heat out, exothermic. So that concludes this chapter. All right. Let me know if you have any questions, and we'll see you in the next one.